In this video I'll talk about how to calculate the volume which we will get when we rotate the graph for a function fx about the x-axis. The video will also contain a few examples where we use this topic. If we have a graph for the function fx, which I have sketched here, and this graph is limited when x is equal to a and when x is equal to b. What will happen when you rotate your graph 360 degrees about the x-axis? Then you will get a volume which will approximately look something like this. Something like this, what we have here. I hope you can imagine that when you rotate your graph for the function fx limited to a and b about 360 degrees about the x-axis, then you will get a solid which approximately look like the one I have sketched here. So the question is, how do we calculate the volume of such a solid? Well, what we actually do is that if we take our starting point in a small piece of this volume which we cut out, a small piece which we can call delta x. So that could, for instance, be here. If we say what we have here is delta x. And then we cut out simply this piece here, and that will give us a small volume which will look something like this here. What we have over here. I hope you can imagine that. Now I have simply cut out this small delta x over here, so this distance here must be delta x. So if we label this specific x value here, xi, that will also be the center of what we have over here, xi. So the radius of this small piece which we have cut out here must exactly be equal to the function value which we have here, which you hopefully can see that must be equal to fx y. So that we can put in here. So how do we calculate the volume of such a piece here? Well, it's actually a small cylinder, as you hopefully can see, and the volume of a cylinder, as you recall, we calculate to be equal to the cross-sectional area multiplied with the height. And the cross-sectional area of such a circle here is equal to pi times the radius squared, and the height here must be equal to delta x as we have labeled it. And since we've just agreed that the radius of this small piece here must be equal to the function value fxy, I can write again that the volume is equal to pi times fxi squared times delta x. So that must be equal to the volume of this small piece which I've cut out here. So the total volume of this solids which we will get when we rotate the graph for fx 360 degrees about the x-axis must be equal to the sum of all the volumes of the small pieces delta x which we could cut out here throughout the graph for fx. So that we can write in a more mathematical way as the volume is equal to, approximately equal to, the sum of, and the volume is generally given for these small pieces by pi times fxi squared times delta x, as we have noted over here. So if we let delta x tend to 0, that is, if we let the small pieces which we cut out being smaller and smaller and smaller, the sum of all these volumes will be closer and closer to the exactly volume of the entire solid here, which we get when we rotate fx about the x-axis. So that must be that this volume here, which we can call Vx, indicating it's the volume which we get when we rotate the graph for fx about the x-axis, to be equal to the limit value when delta x tends to 0, of all this which we have here, the sum and that's what you hopefully recognize as being equal to the integral with the limits a and b pi fxi squared dx. So that's how you can calculate the volume of the solid you will get when you rotate the graph for the function fx with the limits a and b 360 degrees about the x-axis. And you recognize here that this volume will always be positive because fxi squared will always be positive. When you square something, it will always be positive. So it doesn't matter whether it's a positive or negative function. This is how you can calculate the volume when you rotate the graph about the 360 degrees about the x-axis. So let's look at a few examples where we use this. The first example I've chosen to include is this one here, where we have the graph fx equals the square root of x, and in this case we're limited x to be in between 1 and 4. So we should calculate the volume of the solid which we will get when we rotate the graph for fx 360 degrees about the x-axis. So if we start by sketching the graph for fx equals the square root of x, it looks something like this. And since we are only limiting x to be in between 1 and 4, that must be here. That's when x is 1, and here that is when x is 4. So we're looking just at this part here. So when you rotate this graph fx 360 degrees about the x-axis, I hope you can imagine that you will actually get like a coffee cup here. That will be, the volume will look like a coffee cup. So what is the volume of this coffee cup, or this solid which you get when you rotate the graph for fx 360 degrees about the x-axis? Well, that's what we would like to calculate now. So this volume Vx we can calculate as the integral with the limits 1 and 4 of, and then we remember that we calculate the volume rotating about the x-axis to be equal to pi times fx squared, which is this, in this case is the square root of x squared dx. The square root squared will eliminate each other, so what we have left is pi times x dx. Pi is just a constant. We can move outside our integral sign, so what we'll have left is x dx, which we can integrate, so we get pi half x squared with the limits 4 and 1. So what does that give me? That gives me pi, and then I insert the upper limit 4, so that will be 8, minus, and the lower limit 1, a half, so altogether 7.5 pi is equal to the volume which we will get when we rotate the graph for the function fx equals square root of x 360 degrees about the x-axis with the limits 1 and 4. So that was the first example which I have chosen to include on how to calculate the volume Vx rotating about the x-axis. The second example I will include is a bit more complex. In this example, we are supposed to find the volume which we will get when we rotate this small piece here 360 degrees about the x-axis. So this small piece here, which I have squared here, we get when we look at the restriction from 0 to 1 of x, which we have here, of what is limited by the graph for the function fx equals x squared. That's the one I've sketched here. That's part of the parabola, x squared, and the other function which we look at here, which is limiting our volume, will be gx, which is equal to x to the power 3. That is the one which I've sketched here. So these two graphs for fx and gx, they intersect when x is equal to 1, as you hopefully can see. So they will create a small area which will give us a small volume when we rotate this small piece here 360 degrees about the x-axis. So that's what we would like to figure out. What is this volume equal to? If we should do that, we can simply use the formula which we have seen already in this video, that Vx is equal to the integral with the limits. In this case, that must be the limit from 0 to 1 of pi times fx squared dx. The problem is just here that we do not have only one function here, as we saw in the first example. We have two functions, but it's not a problem, because you can just imagine that if you rotate your so-called upper function, the function with the highest function value in the interval, which in this case must be fx equals x squared. If you rotate this function 360 degrees about the x-axis, you will get a certain volume. And if you at the same time rotate the function, which is the lower function in the interval, which is gx here, 360 degrees about the x-axis, then you will get another volume. And if you subtract that volume, which you will get when you're rotating the lower function gx, with the volume you will get when you rotate the upper function fx, then you hopefully can see that then what you will have left will be the volume exactly equal to rotating this piece 360 degrees about the x-axis. So that's what we will do. So Vx must be equal to the integral from 0 to 1 is the limit of pi, and pi is just a constant, so I'll move that out, the integral sign. So the integral will be the upper function squared, which in this case is x squared, so we call that, we could start by saying fx squared subtracted with the lower function squared, which is gx squared dx. So what is that in this case here? Well, that will be fx is given by x squared, so we have x squared subtracted with gx, which is given by x cubed squared dx. So what is that equal to? Well, that is equal to, we'll just continue over here, x to the power of 4 subtracted with x to the power of 6 dx. So now we're just continuing integrating that. So x to the power of 4, that must be equal to 1/5 x to the power of 5 minus 1/7 x to the power of 7, and the limits are still 0 and 1. So now we just need to insert the values here. So what we'll get is pi times, and we insert 1/5 subtracted with 1/7, and 0 will just 0 out. So what we altogether get will be 235 pi, it must be. So that's the volume which we will get when we rotate this small piece here 360 degrees about the x-axis. So the most important thing is to realize when you should rotate a certain area about the x-axis, which is created by two functions or maybe more, is to figure out which one of these functions are the upper functions in this interval and which one are the lower functions in an interval. And then you can jump directly into the formula which we have figured out is equal to the volume rotating about the x-axis and by that get the result. So that's the conclusion of how we can calculate the solids of revolutions when we should rotate about the x-axis. You find the integral with the limits a and b, and then you integrate pi times fx squared dx. That is all for now. If you're wondering how we should find the volume of the solid when we rotate the graph about the y-axis, then look into the video called Solids of Revolution or Rotating About the Y-axis Vy.